Welcome back to the Deep Dive. Ready to explore something truly mind-bending?
I'm definitely up for the challenge, especially if it involves quantum mechanics.
Well, you're in luck. Today, we're diving into the world of quantum programming languages. We're going to try to figure out how to talk to these quantum computers. You know, the ones that are supposedly going to revolutionize everything.
It's a pretty hot topic. And not just for computer scientists anymore, either.
No, I think anyone who even remotely curious about the future needs to understand at least the basics of this stuff. It's like, if we're on the verge of this quantum revolution, shouldn't we know how to speak the language?
Exactly. And that's exactly what we're going to try to unpack today with the help of an essay by Jorgo Schneepat. It's called Quantum Programming Languages, Tools of the Future.
Yeah, Schneepat lays it all out pretty clearly. It's not just about learning a new syntax or a few quirky commands. It's about grappling with an entirely new way of thinking about computation. It's thinking quantumly.
You know, I think that's one of the most fascinating things about this whole field. It's not just about building faster computers. It's about fundamentally changing how we approach problems.
Okay, so let's dive into it. Let's start with the basics. What exactly is a quantum programming language?
Well, think of it as the bridge between our human minds and the very weird, very counterintuitive world of quantum mechanics. It's the set of instructions, the grammar, the vocabulary that we need to tell a quantum computer what to do.
So instead of ones and zeros, we're talking about
Qubits, which, as Schneepat explains, can be a 0, a 1, or, and here's where it gets trippy, a blend of both at the same time.
It's called superposition, right? That's one of the mind-bending things about quantum mechanics.
Exactly. And Schneepat uses a really helpful analogy. He compares it to a dimmer switch. You know, instead of just being on or off, a qubit can be anywhere in between.
It's almost like a quantum computer is capable of exploring multiple possibilities simultaneously.
Exactly. And that's just the beginning. Schneepat goes on to explain the concept of entanglement.
Ah, yes, entanglement. That's where two qubits are linked together, even if they're miles apart.
Miles apart, different galaxies apart, the distance doesn't matter. You change one and the other changes instantly. Einstein famously called it spooky action at a distance. And for good reason.
I mean, it still kind of freaks me out, even though we've talked about it a bunch of times.
I know. It's one of those things that just doesn't quite fit into our everyday understanding of how the world works.
But it's real, and it's one of the key ingredients that make quantum computers so potentially powerful.
Exactly. It's this entanglement that allows quantum computers to tackle problems that would be impossible for classical computers, even those supercomputers we have today.
And Schneepat explains how these quantum programming languages have to be able to create and manipulate these entangled states. It's not easy.
No, it's not easy at all. And then there's another wild concept Schneepat describes, quantum measurement.
Right, measurement. Because, you know, it's all well and good to have these qubits in all these superposed and entangled states, but eventually we need to get an answer out of them.
And that's where measurement comes in. It forces a qubit to choose a definite state. It's like that dimmer switch finally being set to a specific brightness level.
So if superposition is like a spinning coin, measurement is like the coin finally landing on heads or tails.
Precisely. And Schneepat really emphasizes how crucial measurement is for quantum programming languages.
Because that act of measurement itself changes the system, right?
It does. So it's like you're trying to observe this delicate quantum dance, but the very act of observing it disrupts the dance. It's kind of a catch-22.
So designing languages that can extract meaningful results, even with this weirdness of measurement, is a huge challenge.
It is. It is. And on top of all of that, these quantum programming languages also have to deal with the nitty-gritty details of quantum hardware, which is still in its very early stages of development.
Schneepat mentions that the math involved is pretty intense.
Oh yeah, it's pretty hardcore. We're talking linear algebra, complex numbers, tensor products. I mean, it's not exactly something you pick up over a weekend, you know?
So, for our listener, just know there's some serious mathematical firepower behind these languages. But don't worry, we're not going to dive into the equations today.
No, definitely not. But I think it is important to know that quantum programming is deeply rooted in math, and that's part of what makes it so challenging, but also so fascinating.
Totally. But how did we even get to this point where we're talking about quantum programming languages? Was it all just a sudden breakthrough? Like someone woke up one day and said, Eureka, quantum computers.
No, not quite. It was more of a gradual evolution of ideas. Schneepat does a great job of laying out the historical context.
So who are the pioneers? Whose shoulders are we standing on?
Well, Schneppat talks about Richard Feynman, the famous physicist, back in the 1980s. Feynman had this insight that classical computers, even the most powerful ones, were really bad at simulating quantum systems. I mean, they're just fundamentally different kinds of systems.
So it was kind of like, hey, if we want to truly understand this quantum world, we need a computer that speaks the same language. Is that basically what Feynman was saying?
Exactly. Feynman proposed that a computer built on quantum principles would be far more suited for the task. It was a pretty radical idea at the time.
It was a paradigm shift. And around the same time, Schneppat mentions David Deutsch, a physicist who really formalized the concept of a universal quantum computer.
Yeah, Deutsch's work was groundbreaking. He essentially laid out the blueprint for a quantum computer that could theoretically outperform any classical computer we could ever build.
So it was a 1-2 punch. Feynman's insight that we need quantum computers to understand the quantum world, and then Deutsch's theoretical framework for actually building them.
Exactly. And it wasn't long after that that people started developing the first quantum algorithms.
Yeah, Schneppat discusses those early algorithms, things like Shor's algorithm that really shook things up.
Shor's algorithm in particular was a real wake-up call for the cryptography world.
Because it showed that a quantum computer could factor large numbers exponentially faster than any known classical algorithm.
Exactly. I mean, it was a real game changer. Think about it. Our current encryption methods rely heavily on the fact that it's very difficult for classical computers to factor large numbers.
It's like a giant puzzle that would take a classical computer years, centuries, maybe even millennia to solve.
Right. But a quantum computer, thanks to superposition and entanglement, could crack it in a fraction of the time.
So it was kind of a light bulb moment, wasn't it? These quantum computers weren't just a theory. They could actually do things that were practically impossible for regular computers.
Absolutely. Schneppat really makes that point clear in his essay.
And that's where these quantum programming languages enter the picture.
Right, because you can have the most amazing quantum computer in the world, but if you can't communicate with it, you can't give it instructions, it's just an expensive paperweight.
You need a way to harness that power, and that's where the languages come in.
And Schneppat really emphasizes that point. He argues that the shift from focusing solely on building the quantum hardware to developing the software that could unlock its power was a crucial turning point.
It makes perfect sense, right? You build this amazing machine, but then you need a way to tell it what to do.
Exactly. And just like in the world of classical programming, there's no one-size-fits-all solution. There are a bunch of different quantum programming languages, each with its own strengths and weaknesses.
Ooh, a quantum programming language showdown. Okay, I'm ready to hear about the contenders. Which ones are the major players, according to Schneppat?
Well, he starts with Qiskit, which is developed by IBM.
IBM, the big blue giant. So Qiskit, what's the deal with that one?
It's open source, which is great for accessibility, and it's based on Python.
Ah, Python. That's a language a lot of people are familiar with.
Exactly. Schneppat points out that this makes it a good entry point for those who are already comfortable with classical programming. He even calls it the Python of the quantum world.
I like that. So Qiskit's kind of like the gateway drug to quantum programming.
It's a good way to put it. Schneppat explains that it's widely used in education and research, and it has a large and supportive community.
So it's a good starting point if you want to dip your toes into the quantum waters.
Definitely. Then Schneppat talks about Cirq, which was developed by Google.
Google, of course.
Yeah.
Always pushing the boundaries. What's special about Cirq?
Well, it's also open source, but it's designed to work really well with what are called NI-SKU devices.
NI-SKU devices, what are those?
It stands for Noisy Intermediate Scale Quantum Devices.
Ah, got it. Noisy, because they're still prone to errors.
Exactly. They're the most advanced quantum computers we have today, but they're still very much experimental. And that intermediate scale part refers to the fact that they have a relatively small number of qubits compared to what we'll hopefully have in the future.
So Cirq is for those who want to get their hands dirty with the cutting-edge hardware, even if it's still a bit finicky.
Precisely. Schneppat points out that Cirq gives programmers a lot of control over the hardware specifics, which can be both a benefit and a challenge.
It sounds powerful, but maybe not for casual coders?
Probably not the best place to start. Now, Schneppat also talks about a couple of other languages that are a bit more specialized. One of them is called Quipper.
Quipper, what's that one all about?
It's based on a language called Haskell, which is a functional programming language. And Schneppat explains that Quipper is well suited for really complex algorithms, the kind that might use a lot of qubits.
So Quipper's for the quantum programming pros, the ones tackling the really big problems.
I'd say so. Schneppat even says that it tends to be popular with people who have a solid math background, especially in things like category theory.
Okay, so that one's maybe not for beginners. What's the other specialized language Schneppat discusses?
It's called Cirq, and it was developed at ETH Zurich.
Cirq. That's a pretty prestigious institution.
It is, and Schneppat actually seems pretty excited about Cirq. He says it's designed to make quantum programming easier and safer.
Easier and safer. That sounds promising. Sign me up.
Well, Schneppat explains that one of Cirq's key features is that it automatically cleans up unused quantum resources, which helps to prevent errors.
So it's kind of like a self-cleaning oven, but for quantum code.
Haha. I guess you could say that. It's like a programming language that's always tidying up after you.
Now that's a language I could get behind.
Yeah.
But, even with all these amazing languages emerging, it's hard to shake the feeling that this is all still very early days. Like we're just scratching the surface of what's possible with quantum computing.
Absolutely. I think that's one of the things that Schneppat conveys so well in his essay. He acknowledges the tremendous progress that's been made, but he also doesn't shy away from the challenges that lie ahead.
And what are some of those challenges? What are the things that are keeping quantum programming from becoming, truly mainstream?
Well, one of the biggest hurdles is the hardware itself. As we've talked about, qubits are extremely fragile. They're prone to errors. They're easily disturbed by their environment. And we're still a long way from having quantum computers with a large number of qubits.
Right. It's like trying to build a house of cards in a windstorm.
Mm-hmm.
It's incredibly difficult to keep everything stable and working properly.
That's a great analogy. And then there's the whole issue of error correction, which Schneppat emphasizes as being absolutely crucial.
Because even with all those incredible advances in hardware, these quantum computers are still prone to errors. They're not perfect.
Right. So a lot of the work in quantum programming right now is focused on developing algorithms and techniques to mitigate those errors.
It sounds like a constant battle.
It is. And it's not just about the technical challenges either. Schneppat also talks about the need to develop a whole new way of thinking about programming. I mean, quantum programming is fundamentally different from classical programming.
So it's not just learning a new syntax, it's learning to think in a whole new way.
Exactly. It's like instead of thinking in 2 dimensions, we have to learn to think in 4 dimensions, or maybe even more. It's about embracing concepts like superposition and entanglement, which are just so foreign to our classical way of thinking.
It's like rewiring your brain. So it sounds like quantum programming is not for the faint of heart.
It's definitely not the easiest field to jump into, but it is incredibly rewarding, and I think Schneppat does a fantastic job of conveying that sense of excitement and possibility in his essay.
Yeah, there's a real sense of adventure, like we're exploring uncharted territory. Okay, so we've talked about the history of quantum programming, the basic principles, the challenges, and some of the key languages. Where do we go from here? What's next on our quantum journey?
Well, I think the next step is to dive a bit deeper into those specific languages that Schneppat highlights. Let's take a closer look at what makes each one unique, what their strengths and weaknesses are, and what kind of problems they're best suited for.
I'm ready. Let's get specific. Let's explore the landscape of quantum programming languages.
So let's get into the specifics of these languages. Schneppat starts with Qiskit, which, as we mentioned, is developed by IBM and based on Python. He really emphasizes its popularity and how accessible it is.
Yeah, especially for those of us coming from the world of classical programming. Qiskit seems like the most natural place to start. It's like the on-ramp to the quantum highway.
That's a great way to put it. And it's open source, which Schneppat points out is huge for building a community.
Right. It means anyone can contribute, anyone can learn from it. It's all about collaboration and shared knowledge.
Exactly. Schneppat really seems to appreciate that aspect of Qiskit. He even mentions how impressed he is with the vibrancy of the Qiskit community.
It's a good sign. A strong community means lots of support, lots of resources, and hopefully lots of innovation.
Absolutely. Now let's move on to Cirq, Google's framework for those NISQ devices.
Ah, yes, Cirq. It's designed to work with the bleeding edge of quantum hardware, even if it's still a bit temperamental.
Exactly. Schneppat makes it clear that Cirq gives you a lot of fine-grained control over the hardware, which can be great for certain tasks.
But maybe not for beginners.
Maybe not. Schneppat suggests that Cirq is more for experienced programmers who are comfortable working close to the metal, so to speak.
So Cirq's for those who are really pushing the limits, those who want to squeeze every last bit of performance out of those NISQ devices.
Exactly. It's definitely a more specialized tool, according to Schneppat.
Okay, so we've covered Qiskit, which is kind of the friendly, accessible one, and Cirq, which is the powerful but maybe a bit intimidating one. What about Quipper? That's the one based on Haskell, right?
Right. Schneppat highlights that Quipper is really well suited for dealing with complex algorithms and large-scale computations.
So Quipper's for the heavy lifting, the really intricate stuff.
Yes, and Schneppat points out that it's quite popular with researchers who are working on things like quantum error correction and quantum algorithms.
Because those are areas where you really need a language that can handle a lot of complexity.
Exactly. And then there's Cirq.
Ah, Cirq. This is the one developed at ETH Zurich, the one that Schneppat seemed really intrigued by.
Yes, Schneppat spends quite a bit of time discussing Cirq. He's really impressed with its approach to making quantum programming more intuitive and less error-prone.
Tell me more. What makes Cirq so special? So it's kind of like the rebel of the quantum programming world, shaking things up, trying new things.
Yeah.
I like it.
I think Schneppat likes it too. Now, I know we've been throwing a lot of names and acronyms around, but I hope our listeners aren't too overwhelmed.
Yeah, I mean, it's a lot to take in, I get it. But it's important to remember that this is all still pretty new. We're literally just at the beginning of this quantum computing revolution.
Exactly. It's like we're back in the early days of classical computing when everything was still being figured out.
And just like in those early days, there's a lot of experimentation happening, a lot of different approaches being tried out.
And that's what makes this such an exciting time to be involved in quantum programming. There's so much potential, so much still to be discovered.
Absolutely. Okay, so we've got a good overview of some of the key languages out there. What's next? Where do we go from here?
Well, now that we have a sense of the languages themselves, I think it's important to talk about the algorithms, the actual things that these languages are used to create.
Right. The algorithms are where the rubber meets the road, so to speak.
Exactly. Schneppat dedicates a good portion of his essay to exploring these quantum algorithms, and I think it's crucial to understand what they are and what they can do.
Okay, so let's talk algorithms.
Let's start with the classics, the ones that really put quantum computing on the map. Grover's algorithm and Shor's algorithm.
Yeah, those are those we hear about all the time, the heavy hitters. What exactly do they do?
Well, Grover's algorithm is essentially a search algorithm. It can be used to find a specific item in an unsorted database much faster than any classical algorithm.
So instead of having to search through every single item one by one, a quantum computer, using Grover's algorithm, can find the item you're looking for exponentially faster.
Exactly. Schneppat uses a really helpful analogy. Imagine you have a phone book with 1,000,000 entries and you're trying to find a specific person. A classical computer would have to go through each entry one by one until it finds the right one.
Right, that could take forever.
Exactly. But a quantum computer, using Grover's algorithm, can, in a sense, search all the entries simultaneously.
Oh, that's amazing. It's like having a superpower.
It kind of is, and that's what makes quantum algorithms so potentially powerful. They allow us to do things that are simply impossible for classical computers.
So Grover's algorithm is about searching, about finding things quickly. What about Shor's algorithm?
Shor's algorithm is about factoring large numbers, which sounds pretty mundane, but it has huge implications for cryptography.
Ah, yes, we talked about this earlier. It's the one that could potentially break our current encryption methods.
Exactly. Schneppat does a really good job of explaining how Shor's algorithm works and why it's such a big deal. He even talks about the race to develop quantum-resistant encryption methods.
Because it's like a ticking time bomb, isn't it? Once quantum computers become powerful enough to run Shor's algorithm effectively, a lot of our current encryption methods will be rendered useless.
It's definitely a serious concern. But it's also important to remember that Shor's algorithm could lead to the development of new, even more secure encryption methods.
So it's a double-edged sword, a threat, and an opportunity.
Exactly. And Schneppat doesn't shy away from discussing both sides of that coin.
So we have Grover for searching and Shor for factoring. What other quantum algorithms are out there?
Well, Schneppat discusses a bunch of others, including the Deutsch-Josse algorithm, which shows how quantum computers can solve certain problems exponentially faster than classical computers. It's another one of those algorithms that really highlights the advantage that quantum computing can offer.
It's not just about speed, though, is it? It's about the kinds of problems we can solve, the kinds of questions we can answer. It's about opening up entirely new realms of possibility.
Exactly. And then there are algorithms like the quantum approximate optimization algorithm, or QAOA, which is designed for tackling optimization problems.
So problems like finding the most efficient delivery route or optimizing a financial portfolio. Real-world stuff.
Exactly. And Schneepat points out that QAOA is one of those algorithms that's generating a lot of excitement because it has the potential to be applied to a really wide range of practical problems.
I can see why. Optimization is everywhere. And then there's the variational quantum eigensolver, or VQE. What's that one all about?
Schneepat describes VQE as an algorithm that's used for finding the lowest energy state of a quantum system. It's really important in fields like chemistry, material science, and drug discovery.
Because understanding the energy states of molecules is key to designing new drugs and materials.
Exactly. Schneepat even suggests that VQE could revolutionize the way we design new materials and discover new drugs.
It's incredible to think that these quantum algorithms could have such a profound impact on so many different fields. It's like we're on the cusp of a whole new era of scientific discovery and technological innovation.
I agree, and it's all thanks to these quantum programming languages that allow us to harness the power of these quantum algorithms.
It's amazing to think that just a few decades ago, this was all just theoretical. Now we're actually building these machines and writing these algorithms.
It really is a remarkable time to be alive. Schneepat's essay really captures that sense of excitement and possibility.
Yeah, it's clear that he's passionate about this stuff. But it's not all sunshine and roses, right? He also talks about the challenges.
He does. Schneepat is very realistic about the challenges we still face. We've talked about the hardware limitations, the fragility of qubits, the difficulty of error correction.
It's a constant uphill battle.
It is. And then there's the whole issue of cost. Building and maintaining quantum computers is incredibly expensive.
So access to these machines is still very limited. It's not like anyone can just download a quantum programming language and start experimenting.
Right. For now, it's mostly researchers and big companies that have access to these machines. But that's changing rapidly, and Schneepat believes that as the technology matures and becomes more affordable, we'll see a much wider adoption of quantum programming.
I hope so. I mean, it's such an exciting field, and I'd love to see more people getting involved.
Me too. Schneepat also emphasizes the need for more education and outreach. He believes it's crucial to get more people interested in and excited about quantum computing and quantum programming.
I agree. The more people understand this stuff, the better.
Absolutely. And it's not just about training the next generation of quantum programmers. It's about helping everyone understand the potential impact of this technology.
Because this is going to affect all of us, right?
Yeah.
Quantum computing is not just some niche field. It's going to have implications for every aspect of our lives.
Precisely. Schneepat really drives that point home. He argues that we need to start thinking about the societal implications of quantum computing now, before it's too late.
It's like we need to have a conversation about how we want to shape this quantum future. We need to make sure that this technology is used responsibly and ethically.
Exactly. And I think Schneepat's essay is a great starting point for that conversation. He really lays out the issues, the challenges, and the opportunities in a very clear and accessible way.
Yeah, it's a great primer on the world of quantum programming and its potential impact. So we've covered the languages, the algorithms, the challenges, the opportunities. What's next?
Well, I think it's time to step back and look at the bigger picture. Let's talk about the potential impact of quantum computing on various industries, on scientific research, and on society as a whole. Let's explore the future that Schneepat envisions. So Schneepat takes us on this journey through potential impact. He starts by looking at industries, places where quantum computing could really shake things up.
Give me some examples. What industries are we talking about?
Logistics is a big one. Schneepat explains that quantum computers could be used to optimize delivery routes, manage supply chains, things like that, making everything much more efficient.
So no more packages getting lost in the void.
Well, I wouldn't say never, but potentially far fewer. And he talks about finance, too. You know how complex financial modeling can be, all those algorithms, all those variables?
Oh yeah, it's mind-boggling.
Schneepat suggests that quantum computers could be used to develop much more sophisticated financial models, ones that can better predict market trends and manage risk.
So Wall Street might want to start brushing up on their quantum mechanics.
They just might. And then there's materials science, which is a field Schneepat is clearly excited about. He believes quantum computers could revolutionize the way we design and discover new materials.
Because right now it's largely a trial and error process, right? You mix things together and see what happens.
It can be. But Schneppat suggests that quantum computers could allow us to simulate the behavior of materials at the atomic level, helping us to understand their properties and design materials with specific characteristics.
So we could potentially design materials that are stronger, lighter, more durable, maybe even materials with entirely new properties that we haven't even thought of yet.
Exactly. And Schneppat points out that this could have huge implications for everything from building more efficient solar panels to developing new types of batteries.
So it's about solving real-world problems, making things better, more efficient, more sustainable. It's not just about theoretical possibilities.
No, it's about practical applications that could really benefit humanity. And then, of course, there's drug discovery. Schneppat talks about how quantum computers could be used to design and simulate new drugs at the molecular level.
So instead of testing thousands of different compounds, we could use quantum computers to identify the most promising candidates.
Precisely.
Or,
It could drastically speed up the drug discovery process and potentially lead to the development of new treatments for diseases that are currently incurable.
it's amazing to think about the possibilities.
Mm-hmm.
But Schneppat also reminds us that there are potential risks as well.
He does, and one of the biggest ones is the potential threat to cybersecurity, especially with Shor's algorithm looming large.
Right, the quantum codebreaker. It's a serious concern.
It is. Schneppat really stresses the importance of developing quantum-resistant encryption methods and staying ahead of the curve in terms of cybersecurity.
It's like a race against time, isn't it?
Right.
We need to be prepared for the day when quantum computers are powerful enough to break our current encryption methods.
Absolutely. It's a challenge that requires a global effort. And Schneppat believes that collaboration and open communication are key.
Okay, so potential benefits, potential risks, it's all part of the package. But where does Schneppat see all of this leading? What's his overall vision for the future of quantum computing?
Well, he seems cautiously optimistic. He believes that quantum computing has the potential to be a truly transformative technology, one that can solve some of the world's most challenging problems.
But he's also aware of the potential downsides.
He is. Schneppat really emphasizes the need for responsible development and ethical considerations. He argues that we need to start thinking about the societal impact of quantum computing now, before it's too late.
It's about having a dialogue, right?
Yes.
About making sure that this technology is used for good, that it benefits all of humanity.
Exactly. And Schneppat's essay is a really valuable contribution to that dialogue.
Agreed. It's a great starting point for anyone who wants to understand the complexities and the potential of quantum computing.
And he ends his essay with a call to action, which I think is really inspiring. He urges us to embrace the challenges and opportunities of the quantum era and to work together to shape a future where quantum computing is used responsibly.
I love that. It's about taking ownership, recognizing that we have a role to play in shaping this quantum future. It's not just something that's happening to us, it's something that we can actively participate in.
Exactly. And it's not just for computer scientists and physicists either. This is something that everyone should be thinking about, discussing, and engaging with.
Because it's going to affect all of us, one way or another. It's like we're all on this quantum journey together, and it's up to us to decide where we want to go.
I think that's a beautiful way to put it.
Well, I think we've covered a lot of ground today. We've explored the history, the principles, the languages, the algorithms, the challenges, and the opportunities of quantum computing. It's been quite a journey.
It has. And a big thanks to Yurigo Schneppat for providing such a thought-provoking and insightful roadmap.
Yes, his essay, Quantum Programming Languages, Tools of the Future, was a fantastic guide. I highly recommend it to anyone who wants to dive deeper into this fascinating world.
I second that. It's a great resource.
And to our listeners, thank you for joining us on this deep dive into the world of quantum programming languages. We hope you found it as mind-bending and inspiring as we did.
It's been a pleasure.
And until next time, keep exploring, keep questioning, and keep your minds open to the infinite possibilities of the quantum universe.